right, good morning. So today we are going to talk about a new mathematical thing called vectors. Okay, now vectors they differ from numbers because they have both a magnitude and direction. Okay, if you ever saw the movie Despicable Me, okay, vectors have magnitude and direction. Okay. The villain, every time he would say his name is Vector, would say, because I have both magnitude and direction. It's an awesome movie, and it won me from that moment on. Okay, let me talk to you about notation a little bit. We're going to have a vector u, okay, and that's how I write my vectors, is the line with a little hook on it, a little serif. If you want to write a careful vector, okay, a lot of you will write that with a little arrow on it, okay? You could write with a shaded in arrow or not, okay? A lot of times people write vectors just with the line like this, but since I teach a lot of statistics, to me this is U average rather than a vector, okay? I know context matters. I think in England, if you underline something, put a little tilde underneath it, that means to bold it, and that would also, I think, be somebody's vector somewhere. But the textbooks you're going to see are going to use those. Don't look at that. The textbooks you see are going to use these notations. I just use the half arrow. So we have my vector, we have a carefully drawn vector, and then we have probably the vectors you're going to see in books. Okay. All of these are fine for your notation. Okay. It's just that we need to distinguish it from a regular number u. Okay. So how do you write these things? We're going to have a vector u, and we're going to say that's equal to a b. Okay, and we use these sort of angled brackets in order to denote that we have a vector. We have a horizontal part. We have a vertical part. Okay, so for your introduction to vectors, we just deal with vectors and a plane. We deal with two-dimensional vectors. If you wanted to do a three-dimensional vector, then you would just simply add, or we will not be doing three-dimensional vectors, but you would just simply add another letter. If you want to do a four-dimensional vector, or a fifth-dimensional vector, or dot, dot, dot. Okay, so there is no, it can only be this many dimensions. It's however many dimensions you need. Most of your mechanics, your physics classes, you're going to be dealing with two-dimensional or three-dimensional vectors, and higher dimensional stuff you can leave to a later class. Okay, but they do have uses. It's just that not geometric ones. Okay, so we're going to talk about a couple of rules for vectors. Okay, so if we have a vector u, which is going to be a1 and b1, okay, we'll have a vector v, which is going to be a2 and b2. Okay, if you hear the noise in the background, that is one of my cats. She always thinks she has a lot to add to the lectures. And if you hear a 500-pound herd of elephants running through, that is the 5-pound cat because she's got the zips this morning. Okay, so these are our vectors, and then we're going to add them. Okay, so we can say vector addition. Okay, and it's simply going to be a1, right, b1 plus a2, b2. And the way you would add them is exactly the way you think you should add them, is to have a1 plus a2, comma, b1 plus b2. Okay, we add the horizontals together, right? We add the verticals together, and we have our new vector. And I think it's pretty plain to see that since a's are numbers, we could swap the order because we're allowed to do that with numbers. b2 plus b1. Okay, and that is equal to v plus u. So one of the things about vector arithmetic, okay, is that u plus v is equal to v plus u. All right, so that's one property of vectors. There's several. Okay, if we have a u plus v plus w, and let's go ahead and put those two in parentheses, saying that we added these two vectors together, then we could add it to a third one, and this should still be equal to u plus v plus w. Okay, so vectors, they both have the commutative property, they have the associative property. All right, I'm not going to go through proving this one because this follow the same kind of method here, and you're going to be able to do that. Okay, so how you add vectors, we could talk about the analytic way, and this is probably the way you're going to be doing it most of all. We could also talk about the geometric. Okay, am I still in frame? Sort of. We could have a vector, say, u. We could have a vector v, and all we do is we write tip to tail. Okay, if we have this vector and you try to like match up, okay, which is why we don't do this very often unless you have graph paper or very careful about drawing. We match this piece to this piece. Okay, and then we can see that our resultant, okay, that's usually what you call the sum of u and v, is going to be your r vector for resultant. Later in the book, they really go into this. Right now, we're just going to add them and call it the resultant. You can see that u plus v is the same as v plus u, and it makes this little parallelogram thing, but the idea of geometrically adding them, you're going to place the tail of one vector to the tip of the other one, and we're going to end up with our parallelogram that way. Okay, so that's vector arithmetic, and it doesn't matter how many you have. If you have a bunch, if you have a cruel teacher that gives you all of these vectors, and they say, okay, well, go ahead and add geometrically u, v, w, and like s or something, then you've got to do this whole tip to tail business with all of this stuff, and then hopefully, you can make some sort of a polygon out of this thing. And I doubt anybody would ever ask you to do this. I certainly wouldn't, because this is tedious. If I wanted you to add vectors that way, I would give you a list and say, go ahead and add them, because who would ever do this? Okay. Okay, we have vector addition, so we know that vector addition commutes and associates. Let's see here. We have a couple of other rules. We have something called the zero vector, okay, which is a zero with a little arrow on it, which is represented 0, 0. I don't think anybody's surprised there. Your engineering teachers will be very happy if you remember that things are vectors, because when you're doing vector arithmetic, you end up with a vector. So if we have a v plus a zero vector, you guessed it, we got a v as our vector here. If we let's see here, if we take v plus negative v, we end up with the zero vector. Okay, and then we'll talk about a couple of rules here. So that's pretty much vector addition. Okay, then we also have scalar multiplication. Okay, this scales the vectors. So we have some kind of a u. Let's go ahead and give it some actual numbers this time. So let's go with 2, 1. Okay, we can go ahead and graph that. So that's going to be 1, 2, and 1. And you'll please excuse my scaling on here. If I'm going to multiply it by some scalar number, which is what you've dealt with up until now, is just numbers. Okay, so what if I wanted to do something like 3 times u? Well, that would be 3 times 2, 1, and we'd end up with 6, 2. We'd end up with the vector 6, 2. Okay, so 1, 2, 3, 4, 5, 6. Okay, and 1, 2, and this is going to look terrible. Okay, so here's my u. Okay, and your books, many books have much better pictures than this. Okay, and this would be 3u. Okay, so again, it's changing the scaling of the vector, which is why we call it a scalar, and we'll talk about some rules with scalar multiplication. Okay, so if I have a scalar, which is just a real number, okay, just a real number, c, okay, and vectors u and v, okay, then we could say that the scalar c plus C times U plus V, and this is exactly how you think it should work. And that's how that works. So a lot of the properties that they show you in the book, they're I won't say they're common sense because they are definitions for how this should work. So they're setting up a system, but there's nothing really surprising about how any of this really works. One thing you will notice is that I never talk about what is a vector times another vector, and I don't want to write any sort of times in here because we'll get into this much later. We could write the multiplication as a dot. We could multiplication as a cross, as the x, like you did in third grade. And these have names. We have u dot v, and this is defined as a dot product, and this has one rule for multiplication. And then we have u cross v, and this is another rule for multiplication. So as far as scalar multiplication goes, nothing too out of the ordinary. As far as arithmetic goes, nothing too out of the ordinary. I will warn you that if you have the scalar u times a vector, then we end up with a new vector. But since we're multiplying it by 0, that vector is now the 0 vector. Okay, and if we have c, a scalar, times 0 the vector, we still end up with 0 the vector. Okay, so it's important. Your engineering teachers will be very pleased with you if you write 0 as a vector. Your abstract algebra teacher, if you ever end up taking that class, or your vectors class, which you very well might take, will be very happy with you if you remember that 0 as a vector is different, right? Is different than 0 as a scalar. Okay, so this has a magnitude and direction. The magnitude is 0. The direction is 0, which doesn't have a direction, but it's different than the 0 as a scalar. Okay, and it's a little bit weird to explain why that goes in, but they are happier. Okay. So let's talk a little bit about representation and some of the tools you have to do your problems. Okay, so one of the things we talk about is unit vectors. Okay, and unit vectors are special because they have a length of 1. That's what unit in this situation means. Unit means length of 1. Okay, and there's 2 special unit vectors that we can bring in right off of the bat. Okay, we have the unit vector of 1, 0, and this is called I hat. We have the unit vector 0, 1, and that is called j hat. Okay, I usually don't dot my i's with j's. I just let the hat deal with that serves as the dot. If you were going 3-dimensional vectors, you would have 0, 0, 1. Okay, that would be k hat. We don't really deal with other hats after that. We use a different notation. If you have like a 17-dimensional vector, we would do something a little bit different. We'd use a different notation. We'd use E1, E2, E3 to talk about the unit vectors for the first component, the second component, the third component, and so forth. Okay, but again, we don't deal with that. We don't even deal with this. Okay, but I hat is either a 2-dimensional vector, which we'd have 1, 0, or a 3-dimensional vector 1, 0, 0. Okay, J would be 0, 1 for 2-dimensional, or 0, 1, 0 for 3-dimensional. Okay, and we'll talk about changing. Your book has you do this all a lot. It's you have a vector 4, -3, and they say write in unit vector form or write in component form, and that's really all they want you to do is to write this as 4 hat minus 3 j hat. That's what they're saying. And again, stuff that lies on a horizontal, stuff that lies on a horizontal, stuff that lies on a vertical, stuff that lies on the vertical. Okay, and that's what we're doing with that. Let's see. If we go ahead and graph this one, okay, I can make myself a better graph. 1, 2, 3, 4. 1, 2, 3. I picked 4 and 3 for a reason. We can go ahead and graph this. Okay, and you might notice, since we're taking a trigonometry class, that we could represent this as a triangle. Okay, we have a side of 4, we have a side of 3. One of the things they're going to ask you is, what's the length of this vector? What's the length of this vector? And like I said, hey, we got a triangle here. There might be some kind of relationship between the two sides and this slanty side here, hypotenuse, right? So to figure out the length, we'll call this u. To figure out the length of u, okay, the notation for the length are these double brackets here. And we're going to say that this is equal to, and it's the same as Pythagoras. Okay, we're going to say this is 4 squared plus negative 3 squared. If you're typing this in your calculator and it gives you a negative, don't believe it. It's lying to you. Okay, you know better than a calculator. And we end up with a length of 5. Okay, and similarly, we could also get that angle, right? It's opposite over adjacent, so that angle is going to be the inverse tangent, right, of what do we have here? We have negative 3 over 4. Okay, so that's another way to write a vector, is its magnitude and direction. So we could have, we could have 5 at, and I guess it's going to be like something like negative 53 degrees. That would be an appropriate way to write a vector as well. Okay, so we have component form. I don't really know what this form is called, but I guess magnitude direction form. But they're all good. And if you wanted to write the brackets, okay, let me warn you that those brackets are not universal. That's what I always used, but I have seen books and teachers that use regular parentheses when they really meant to use some kind of a bracket for a vector. Don't be too hard on people. That's not a standard notation everywhere. Okay, write this, you always meant plus, but that's standard. This is not standard. Okay, but it's very common, very, very common. So let's do an example. Okay, let's find a unit vector. Okay, in the same direction as a regular given vector. Okay, so if we have a w, okay, which is equal to let's see here. Let's go with 3, negative 2. Okay, and it said find a unit vector in the direction of w. So what we're going to do is we're going to say that the length of w is equal to square root of 3 squared plus negative 2 squared, which is going to be 9 plus 4, which is the square root of 13. What we're going to do is we're going to multiply w by a scalar 1 over root 13, because that's the length. If we multiply the vector and divide it by its length, we should have a length of 1. Okay, 3, negative 2, and that's equal to 3 over root 13 I hat minus 2 over root 13 j hat. And again, I know I talked to you guys about the fact that this is last century's problem here, where we rationalize the denominator, but I think your book is kind of maniacal about making you do this. So we'll go ahead and do it just for the sake of rationalizing our denominator. What I'm doing here, just in case you've forgotten, or maybe you're a new person, you're watching this, this is root 13 divided by root 13. That's 1. We can always multiply something by 1. If I multiply root 13 by root 13, we end up with 13, and then we just have a mess on top. Okay, so that's how I got the 3 root 13 over 13 I hat minus 2 over 13 root 13 j hat. Okay, but that's the length of this. That's the unit vector. A lot of times they'll say write a new vector. We'll say u in the direction of w, and your book will write it this way. That's fine, and your book isn't wrong to write this, and there are a couple of books that use instant adhesion. You're going to find when you're dealing with unit vectors a lot, because you're going to scale them to what you need. Because way back up here, we use the hat notation for denoting a unit vector. I always just ended up writing my unit vectors with a hat rather than a vector, rather than an arrow, to denote that it's a unit vector. So that's the way I'll do it. Your book will write it this way. That's fine. This to me just seems a bit shorter, and since you will deal with a lot of unit vectors in your future, this is just a little bit easier to go with. Okay, so that gives us at least an intro to vectors, and I will set you off to do your homework. The homework for the sections typically involve a lot of numeric work where you're just getting used to the idea of adding the components of two vectors, subtracting the vectors, geometrically dealing with the fact of on graph paper of adding them tip to tail. There's just a lot of practice getting used to the notation and the arithmetic. And it's kind of a long process. It will seem a little bit tedious, but this does lay a foundation for you to do better in physics and better in engineering classes. So the more comfortable you are with adding vectors and multiplying by scalars, the easier your future is going to be. Okay, so I'll leave you with that and set you off on your homework. Okay, thank you.